Well, hello guys, Mr. G here, and today we're going to be doing another video for the grade 12 related to work, energy, and power. These are some questions that mostly I took them from a book called Mind the Gaps, but not all of them are from there. Some questions are from previous question papers and so on. Anyway, we're going to start, but before that, please don't forget to subscribe for the channel so you can get the notifications, you can get the worksheets and more things I post on regular basis. So we're going to start, and this first question is state that a box of mass 100 kilograms slide down a slope, its velocity increased from 0. So here you can see that the initial speed or velocity of the object is 0 meters per second and increase at point A, increase to 4 meters per second at point B. So this box will reach this point at the bottom of the incline with a velocity or speed which is equal to 4 meters per second. In this case, we're going to use the speed, the magnitude of that velocity. Calculate the work done by the non-conservative force while it slides from A to B. The work done by the non-conservative force here will be the frictional force. There is a video related to conservative and non-conservative forces. I'm going to leave the link up here so you can recall about conservative and non-conservative forces. But in this case, the work done by the non-conservative forces is equal to the work done by friction, because all they want is to calculate the work done by the non-conservative force, which is friction here. Now, to answer this question, there are two very simple ways of to answer this question. One of them is the work energy theorem. We can actually use the work energy theorem. Remember that the net work is equal to the change in the object's kinetic energy. This is one option we can actually use. The other option is to use the law of conservation of energy, which is say that the work done by the non-conservative forces is equal to the change in kinetic energy plus the change in potential energy. Now, before we carry on, we said that the non-conservative forces we have here is the frictional force, but let's make sure by making a free body diagram as usual to see what forces are acting there in actual fact. So when we come here, what forces do we have? First of all, we have weight, which is a conservative force. That is weight, and remember it is a conservative force. We have normal. Normal is a non-conservative force. However, the normal does not do work here, but it is a non-conservative force. Be careful with that one. And then we have friction in this direction, which is the non-conservative force. So the work done by the non-conservative force, in other words, will be the work done by friction plus the work done by normal. But the work done by normal is equal to 0 because normal does not do work. So in other words, we are looking for the work done by friction, and we can use those two methods. Let's start with the law of conservation of energy, and then I think you can go and try to do the work energy theorem. We're going to combine during all these questions both ways of doing or answering different questions. So let's follow this method that you can see there. So then here we can say that the work done by friction, which is the work done by the non-conservative force, is going to be equal to half mass final speed square minus half mass initial speed square. This one is quite long, so I hope it does fit in your paper. And this is mass g, or acceleration due to gravity, final height minus mass acceleration due to gravity initial height. Now all this one, we have enough data to substitute for every single thing here, so we don't have to struggle looking for anything. Everything is given to us. So the work done by friction, and then we are going to substitute everything because we in actual fact have everything. Note that this is the initial speed of the object, which is 0, so everything there is 0 because the object starts from rest. As well as here, this is the final height, the product of final height times mass times acceleration due to gravity, so all that is 0. Final answer is 180 joules. Negative, remember that negative means that is not in opposite direction, but energy is being taken away from the system. My advice now, guys, is to try to do it using the work energy theorem, which is right in this side. But the first question is done and dusted. It's quite simple. This is how to apply the law of conservation of energy to this specific question, and the answer is negative 180 joules. Let's go to the next question. Now, the next question say a 2 kilogram block initially at 4 meters height. So the height here, let's start adding the data, is 4 meters here. And the mass of this block is equal to 2 kilograms. And note it's the same block all the time. So it's 2 kilograms there. Its release means that the initial speed here is equal to 0. It's being released, it was not moving downhill from rest on a frictionless ramp. So there is not friction on this ramp, which I'm going to mark here. All this area here is frictionless up until there. There all the time the frictional force is equal to 0 at that on that surface all the time. It then moves on a 10 meters length rough surface. So from here, from this point to this point, there is friction. From there is friction, and the coefficient of kinetic friction there is given to us, which is equal to 0,2, no unit, until reach a rough ramp with the same coefficient of friction. So this one is also friction, there is also friction, it's rough up until there, which have the same coefficient of friction. That coefficient of friction is the same everywhere as from that side. With the same coefficient of friction as light on it 2 meters until it stops. So the speed here is equal to 0. That is what we get there. That is the idea. State the law of conservation of mechanical energy in words. And this one is question 2.1. So this law says that the total mechanical energy in an isolated system remains constant. In other words, mechanical energy does not change. Therefore, the change in mechanical energy is equal to 0. And this could actually be the starting point of the law of conservation of mechanical energy. In other words, the total mechanical energy initial is equal to the total mechanical energy final. This is in symbol the law of conservation of mechanical energy, guys. It is quite important. It is going to be in the exam, so please try to learn it. Use the law of conservation of mechanical energy. So you have to use this law we are speaking about here to calculate the speed of the block at the bottom of the ramp. So we have to know what is the speed of the block at this point, and this, guys, is obviously going to be the same speed that is going to be at that point. We have to use the law of conservation of mechanical energy, and for this one we're going to use the starting point here and the final point there, which is what we are going to be doing now. So we are going to start from there. As I said, the change in mechanical energy is equal to 0, which means that the total mechanical energy initial is equal to the total mechanical energy final. The initial is going to be the starting point, and remember, just for control, that mechanical energy is the addition of kinetic plus potential. So in other words, we come and we substitute in this equation, we actually going to have that the kinetic or total kinetic energy initial plus the total potential energy initial is equal to the total kinetic energy final plus the total potential energy final. That is important, and that is what we are going to do now. Once more, just to recall But all these formulas are given to you. Kinetic energy is half the product of mass speed to the power 2, and potential energy, the one we are working here, is mass acceleration due to gravity height, and we have to substitute each of them within this equation. The guys is quite simple. So if we substitute everything we have all the data, nothing difficult, nothing out of the normal substitution here. So the final is equal to 8,85, let's fix that comma there, 8,85 meters per second, and that is the answer for this other question here. Okay, so we're going to the next one, question 2.3, state the work energy theorem in Word. And this theorem states that the net work done on an object is equal to the change in kinetic energy of the object. In other words, the net work done is equal to the change in kinetic energy. This is the work energy theorem. It is going to be very important, so we're going to use it all the time. In this question, say use the work energy theorem to calculate the speed of the block when past point B. So here at the end of the ramp, in actual fact, it seems like in this question we are not going to use this part of the question for anything. So we're going to question 2.4 and 2.4. This one was question 2.2. You must fix the numbering, it is important, and we're going to be doing question 2.4 right here. 2.4, they say use the work energy theorem, so we're going to obviously start with the work energy theorem. Net work is equal to the change in kinetic energy. Now, to know this one, we're working with this horizontal plane there, that side there. So we need to do the free body diagram. It's always been done. It is one of the steps when you're solving this type of question. So please, I recommend it again to do it. The object is moving in that direction. This is the direction of the displacement as well. This one is the y-axis, and then the forces we have here on the horizontal surface. Remember, we're working on this horizontal surface because that is point B there. At the end is frictional force in this direction. In the opposite direction there is weight, and there is normal on top there. So these are the forces that are acting on that object. The work done by normal here, you can already say the work done by normal is equal to 0. The angle is 90 degrees, and the work done by weight on this side of the work is also 0 because the angle is 90 degrees. But the work done by frictional force, you'll have to calculate it. You can see that the angle there is 180 degrees. So in other words here, you know that the work done by frictional force will be equal to frictional force multiplied by the displacement multiplied by the cosine of 180 degrees. This is how to calculate the work done by frictional force. It is not the first time we do something like this. So if we substitute the formulas on this side here, guys, the only issue here is that you don't have frictional force. You don't have frictional force. Remember, we did many questions in the videos. If you've been following me, we did many questions in which you have to calculate the frictional force. So real fast here, frictional force is equal to the kinetic coefficient of friction multiplied by normal. And we have still another problem. We do not have the normal. We don't have the normal, but we know how to calculate the normal. Again, I said please, I've done many videos of how doing this one. For the normal, we are going to go to the free body diagram, and we are going to be working in the y-axis because the normal is in the y-axis, and the only forces acting on the y-axis is the normal and the weight. So if you apply Newton's first law, you have that net force is equal to 0. You do not have to start from here, guys. This one will say that the normal minus weight will be equal to 0. Normal is equal to weight, and then normal is equal to mass multiplied by acceleration due to gravity. Now, important, this is not a formula for normal. Normal don't have a formula, so you do have to do this one all the time, guys. So this one is 2 multiplied by 9,8, and then the normal was going to be 19,6 Newton. That number must be substituted in there, and then you have that the frictional force is equal to 0,2 multiplied by the normal, which was 19,6. So this is how to calculate the normal. I didn't want to go to a new page for this one because it's work that we did many times. So when you multiply that one by 0,2, it will give you 3,92 Newton, and that will go back here to be substituted in frictional force. So now we actually have all the data. So now we can substitute everything. This one is 3,92 multiplied by the displacement, which is 10, multiplied by the cosine of 180 degree, and this is equal to half. The mass is 2. The final speed is what we are looking for. This, remember, is not the same as this speed. We are looking for the speed at this point B, which is at the beginning of the ramp. If you read the question, it will tell you the minus the half. The mass is 2, and the initial speed now is this one. This one become the initial speed for the next question, guys. So this one is 2 multiplied by the initial speed, which is 8,85 to the power 2. And this will give you final answer of 6,25 meters per second. Guys, this is the answer, the final answer for question 2. I hope you understand. It's not that bad. It's a little bit more work than the beginning, but it's not that bad. Let's go then to question 3. Now, this question says a toy track mass of 1,4 kilogram moving down an inclined track has a speed of 0,6 meters per second. It is shown in the picture. At point P, which is at a height of 1,5 meters above the ground, level QR. So here is the height that you can see there on this side. This is the height of the track. The curved section of the track PQ is 1,8 meters. When the track reaches point Q, it has a speed of 3 meters per second. That one is not given here, so let's write the speed at this point is 3 meters per second. There is friction between the track and the track. So here is frictional force on the surface. On the surface is friction, which they don't mention how much is it, but there is friction, so it's different to 0. Let's write it in that way. State the principle of conservation of mechanical energy, where you can see that this question is for 2 marks and is exactly the same, guys. I am not going to write it. You are going to go back in the video and see the in question 2.1. So I'm just going to write here same as 2.1, so you can go there and look. Is mechanical energy conserved and explain? Well, that is a different question. Is it conserved? No, it is not conserved. Why is not conserved? Well, guys, there is friction, and if there is friction, the system is not isolated. The system is not isolated. That is the answer for that question. And question 3.3, assume that the average frictional force between the track and the track is constant along PQ and calculate the average frictional force experienced by the track and the move along PQ. Do not get intimidated by the word average here, guys. All we have to do is to calculate the frictional force. Forget about that average. As from now, it's going to be like it's going to be constant for us. That is what they meant there. So we're going to start doing it with the law of conservation of energy. For this question, it's quite simple, guys. So we're going to say that the work done by the non-conservative forces is equal to the change in kinetic energy plus the change in potential energy. That is the beginning of the law. If we go back here and we do quickly the free body diagram, the forces that are going to be acting there are a friction pointing in the opposite direction of motion, in this case normal, which is perpendicular to the surface, and then weight, which is going to be pointing in this direction there. Now here, the angle between the friction and the displacement is going to be 180 degrees as usual, we know that, and the angle between the displacement and weight is this one here. You don't need it for the law of conservation of energy, but I'm helping you in case you are doing the other method. This one here is the angle of inclination, but the angle of inclination, note the following, is not given to you. This angle here, you don't know it, but it doesn't mean you cannot calculate the angle. You are possible to calculate the angle because you have this side, which is 1,5, and you have this side here, which is 1,8 meters long. So it's not a problem. So this one here will be 90 minus theta in this case if you want to calculate using the work energy theorem, but it's not the case that we are doing here. So the work done by the non-conservative forces here, which one are the non-conservative forces in this diagram? They are friction and there is normal. So the work done by normal plus the work done by friction, that is the work done by the non-conservative forces. This is equal to half the mass multiplied by the final speed square minus half the mass multiplied by the initial speed square. Note the following: the initial speed is not 0 because the object was moving when starting the motion at 0,6 meters per second. Be careful with that one. Plus mass multiplied by the acceleration due to gravity final height, which is 0, minus mass acceleration due to gravity, the initial height, which is known by us. So now here, if you substitute okay guys, here all this one is 0, the final height is 0, so I'm only going to substitute the initial height. Now, from here, we are going to calculate the frictional force. This point is equal to friction multiplied by displacement multiplied by the cosine of 180 degrees. If you substitute, and this is the magnitude of the frictional force. So this is the end of this question 3. There is the magnitude of the frictional force. Let's see question 4. We're almost done. We have 2 more questions, but they are going to be almost the same. Now, this question 4 say a boy of mass 55 kilograms is traveling. The mass of this boy is equal to 55 kilogram. It's traveling at 6 meters per second. The speed of the boy here is equal to 6 meters per second on a skateboard of mass 1 kilogram. So the mass of the skateboard, be careful with this one, is equal to 1 kilogram. This is of a skateboard. I'm going to write just an S there, and this one is for boy. I'm going to write a B there. When he reaches a ramp of 8 meters, this is the ramp which is 8 meters of length, and he keep moving and reach the top of the ramp with a velocity of 1 meters per second. So the velocity at this point is 1 meters per second. The constant friction that he expected is 6 Newton. So the frictional force throughout the whole motion is equal to 6 Newton, guys. Explain whether his mechanical energy is conserved or not. The answer is no, and the explanation is in question 3.2 here. Is the same question, so we are not going to repeat here. We're going to write same as in question 3.2. You can go back there in the video and see the explanation. Calculate the kinetic energy of the ball when it reaches the ramp. So the kinetic energy at this point here, that is the question. And then the kinetic energy is going to be equal to half multiplied by mass multiplied by speed to the power 2. Now, important, the mass here is going to be equal to the mass of the boy, which is 55, plus the mass of the skateboard, which is 1, and all that multiplied by 6 to the power 2. Guys, very simple calculations, and that will give 1008 joules. That is the answer for the question 4.2 here. Question, calculate the height of the ramp. And to calculate the height of the ramp, again, is two different options to calculate here. You can either use the law of conservation of energy, or you can also use the law of the work energy theorem. In this case, I think we can use either one, but if you use the work energy theorem, is more work. So let's use the law of conservation of energy once more. And we're going to start from here, because we've been doing this question now for the fourth or the third time, so it's not a big problem. We have, in actual fact, everything here. All we have to do is to substitute. And when you do this calculation, you get that the height is equal to 1,7 meters. This is the end of question 4.3. I hope you understand. I think after this video, you won't have any more problem with any question related to law of conservation of energy or work energy theorem. Now, question 5, which is the last one, we're going to see that is almost the same question. All of them say John applies the force F to help his friend in a wheelchair to move up a ramp of length 10 meters. The length of the ramp is 10 meters. You can see it here written in the question there. And a vertical height of 1,5 meters. The height is 1,5 meters, shown in the diagram below. The combined mass of his friend and the wheelbarrow is 120 kilograms. The mass here is equal to 120 kilograms. The frictional force between the wheels of the wheelchair and the surface of the ramp is 50 Newton. The frictional force is equal to 50 Newton. The rotational effect of the wheels and the wheelchair are ignored. This is important. We are not going to be doing rotations here, so it's important to know that the rotational effect is not taken in consideration. The wheelchair moves up the ramp at constant velocity of 1,5 meters per second. It is very important statement here. The velocity is constant and equal to 1,5 meters per second. Velocity is constant there. What is the magnitude of the net force acting on the wheelchair as it moves up the ramp? Give a reason for your answer. And guys, it's very simple. The net force is going to be equal to 0 because the velocity is constant. What is the magnitude of the net work done on the wheelchair on reaching the top of the ramp? And the net work is equal to 0. Remember that net work is equal to F net multiplied by the displacement multiplied by the cosine of theta. But if F net is 0, so is the net work. So if the net force is 0, so is the net work. This one is quite simple. Calculate the following: work done on the wheelchair by the force and the magnitude of the force F exerted on the wheelchair by John. And once more, to do this one, we are going to start by drawing a free body diagram to see all the forces here. In this case, there are more than one non-conservative forces here. This is the displacement, or it's the x-axis, whatever you want to call it will be fine there. This is the y-axis perpendicular to the x-axis. And if you draw the free body diagram here, you have the applied force up in this direction. This is the applied force. We have weight which is pointing straight down. We have normal force which is perpendicular here, and we also have the frictional force. Guys, note the following: we don't have the angle of inclination, so if we want to work with certain things here, it may be a little bit tricky there, but this is what we have now. No conservative forces acting here. The applied force, this is a non-conservative force. We have the normal force, which is a non-conservative force, and we have the frictional force, which is a non-conservative force. Those three forces are non-conservative. So we're going to be calculating the work done on the wheelchair by the force F. And to do this one, we are going to be using the law of conservation of energy again. So now here we are going to go and say I want you to note something here. This is 0 because the speed is 0. The speed is constant, so the kinetic energy in actual fact does not change. So all that is 0. And if we carry on here, this is final, this one is initial. The initial potential energy is also 0 because it's starting from the surface. So saying that, we are making it much shorter. We have that the work done by the applied force plus the work done by frictional force is equal to a final potential energy. Let's first calculate the work done by friction. Work done by friction is equal to frictional force displacement multiplied by the cosine of 180 degrees, and when you substitute here, and the potential energy here is equal to mass acceleration due to gravity final height and here we are. If we substitute everything in the equation that we have left here, that is the answer of that specific question. Quite simple. And then the final question here is calculate the magnitude of the applied force. All we have to do, this one is question 5.3.2, is to substitute in the formula of work done by the applied force, which is equal to the applied force displacement multiplied by the cosine of theta, but this is 0 in this case. If you go to the free body diagram, you can see the direction of the angle between the applied force and the displacement is equal to 0. So if you substitute here, you have 2000 and the applied force is equal to 226.4 Newton. Guys, with this we end this video. So this is few questions. I think after this one you should not have any problem with the topic. I hope it helped. If it helped, please thumb up, subscribe for the channel. I'll see you next time. Mr. G here.